Hello everyone, I'm Vincenzo from Okinawa Institute of Science and Technology, and today I'm going to talk about the structure-property relationship of soft colloidal glass in simple and mixed flow. This is a joint work where Stelio and John helped us from the University of Patras in Greece to perform numerical simulation of this system. And just a little bit of introduction, colloidal rods are ubiquitous in many fluids such as cream and lotions, and especially for increasing the viscosity of the suspension, so effectively acting as a rheological modifier. And they are way more efficient than a hard sphere at increasing the viscosity, and therefore they are way more appealing from an industrial perspective. And in real life condition, this colloidal suspension will be exposed to most often to shear flow and as well extensional flow. However, for real application, there will be always a mixed flow condition where shear and extension will always coexist. And understanding the rheological property in this mixed flow condition is very crucial, and sadly we cannot rely on the rheometer as we do for shear flow. And understanding this mixed kinematics, mixed flow condition is very important also for the production of anisotropic soft solid. For instance, when we extrude some colloidal rods through a nozzle, there will be acceleration of the fluid producing extensional flow, but there will also be some shear component near the edges. And what happens is that the combination of shear and extension will give rise to some sort of alignment of these rods, and therefore to a specific structure of this filament, which will be material, and the structure will give specific functionality to it. And here we see the birefringence image, so that where the rods are aligned, there is more birefringence. And the building block of our system is cellulose nanocrystal, which is biodegradable but also naturally derived colloid, and is very polydispersed in nature, as you can see the length and the diameter distribution over here. However, we can find an average length of 260 nanometer and roughly 5 nanometer in diameter. And it's important to mention that this system is electrostatically stabilized due to the negative charge on the surface of these rods. And it's very important to mention that according with the concentration, which here is in this graph is expressed as Onsager dimensionless concentration that accounts for the length and the diameter of the rods. And according with ionic strength, in this case the sodium chloride, we can form different phases using these colloidal rods. And Xu et al. Published this very nice phase diagram where you can see that the material can go from an isotropic state to repulsive glasses by just increasing the concentration, but can also go from isotropic to gel phase, just increasing the ionic strength and decreasing the charge on the surface. A more generic phase diagram was published by Solomon and Spicer in Soft Matter more than 10 years ago now, and they presented the phase diagram as function as a volume fraction as function of the aspect ratio of the rods, and they classified the gel and the glassy state. And so the gel state for a given length and diameter, so for a given aspect ratio, the gel is formed at a lower volume fraction than the glass, as you can see here. So in this system, we are going to focus on the cellulose nanocrystal at this concentration, that is 2 weight% at 25 millimolar sodium chloride. And at this ionic strength, the charge, the repulsion, and electrostatic attraction are kind of balanced. And therefore, we, according with Xu et al., end up in this phase, which is called liquid crystal hydroglass. And according with Solomon and Spicer, we are in the glassy state. So this is very appealing material because it produces some anisotropic domain, which are the nematic domain, and therefore when we see the material and the cross-polarize the lenses, we can see this rainbow pattern. However, this material is also a yield stress fluid, and therefore there is some sort of network formation. And therefore the material, when for instance in this cuvette, when we place it upside down, it's able to retain its shape, and it doesn't flow under the effect of gravity. So we can conceptualize the material as a network embedded as a nematic domain embedded in a network, where the network gives rise to the yield stress property and the nematic domain to the birefringence. And so at this point we can establish the purpose of our talk, that is understanding the structure property relationship of this material, which is a colloidal glass in simple and mixed flow. So we begin with the classical oscillatory rheology experiment. First of all, we reach the equilibrium state. So first apply a pre-shear, and then we apply some very tiny oscillation in such a way that we don't destroy the material. And we see that G prime and G double prime after almost 2 hours reach kind of a steady state. And then we can perform some frequency sweep, and then we can perform also some amplitude sweep. So in the amplitude sweep, when we increase the amplitude, the material gets destroyed, and therefore it yields, and G prime becomes lower than G double prime, meaning that the material in this region, which is often referred to Laos region, the material acquires its liquid like nature, while in this other regime the material is solid-like. And also in the frequency sweep we can observe that the material is mainly elastic. Indeed, G prime is greater than G double prime, and it shows a kind of fingerprint of a gel, where G prime and G double prime are pretty much independent from the angular frequency. At this point, we introduce the thixotropic elastovistoplastic model, TEVP, which is given by the lines. And this model will help us to understand where we cannot perform experiment about some structural and rheological property of this fluid. So what we do is to fit this data with this TEVP constitutive model, and this model feature 10 parameters, but for the sake of this presentation we're going to focus mainly on 2 of them, which is the yield stress given by tau y, and lambda, which is a structural parameter. And especially lambda is a very important parameter, as we can see over here. So, and what we do first, we study the material and the rheometric flow, simple shear flow, and we measure the tau xy, the stress as function of the shear rate. There are 3 distinct regimes that are nicely captured by the TEVP model, and what we see is that we can basically interpret these 3 regimes in terms of lambda, which is the structural parameter given by the model. And lambda attains its maximum value of 1 in the low shear regime. However, it starts to decrease, meaning that the material starts to break upon shear and attains its minimum value, which we call lambda infinite, which corresponds in this case to the fully disrupted material, where the colloidal rods are free flowing. And in uniaxial extension, we cannot perform reliably these measurements, and therefore we rely on the model. And this is a first instance where this model can provide us some supplementary information which we cannot access experimentally. And so we see that the extension of viscosity is a strong function of the extension rate, and especially is extensional thinning. And this behavior is completely the opposite behavior of what we observe in polymeric fluids. And again, lambda resemble pretty much obtained in extensional resemble pretty much the one we have shown in shear. And at this point, we can proceed with microfluidics, where we can study the extensional flow using the optimized shape cross-lot extensional rheometer, OSHR, where the material is injected through the inlets and will be compressed, and then will be extended along the outlets. And this geometry is, let's say, an evolution of the simple cross lot, but is optimized at the edges with these squared corners in such a way that hyperbolic corner in such a way that the material for a Newtonian fluid it predicts to have a pure extensional flow in a great area, in a large area around the stagnation point, that is the center of the geometry, where the velocity is zero. And so this Oscar device is used to produce extensional flow. And the mixed flow condition, for the mixed flow condition, we use a microfluidic cylinder device that is a simple microfluidics device with a rectangular cross section that contains a little cylinder, and this cylinder pretty much will develop some in the flow field some extensional component in the rear and the front pole of the cylinder, but also some strong shear component at the sides. And in this case, there will be always some sort of mixed kinematics, and therefore it's perfect for our purposes. And I want to just point out that this geometry is pretty much the 2D version of the falling sphere benchmark test that is usually done in non-Newtonian fluid mechanics. And what we use to control the flow is the Weissenberg number that accounts for the velocity generated in the channel, as well as the length scale of the geometry. So in the extensional flow, we start with the Oscar, and we can see that using particle imaging velocimetry, where we measure the velocity in the channel. There is a good agreement between experiment and simulation, and so at this point we can understand something more about the material in the channel, and we use the simulation given by the TVP model to predict where the material is in the liquid and in the solid state. We see that the material in most of the geometry is in the liquid state, so given in red. However, there are some regions, symmetric for region given in blue, where the material is predicted by the model to be in the solid state. And we can conceptualize the presence of these solid-like regions by the fact that the material enters in the liquid state, given in red, following the arrow, and then the stress substantially decreases, and so allowing the material to regain its solid-like property. However, then exiting the geometry, the stress increases and the material regains its liquid-like property. And we use birefringence as a complementary experiment. In this experiment, the alignment of the rods is measured, the extent of alignment, and pretty much is given by this color code. And we see that when very high retardance or very high birefringence is present in the material, the model predicts that is in the liquid state. However, when the material show very little birefringence or little retardance, the model predicts that the material is in the solid state. And we can understand this by the fact that the rods can align when the material is in the liquid state. However, the rods cannot significantly align when the material is in the solid-like state. And also comparing the simulation and the experiment, we see that the simulation predicts a shrinkage of these four regions of a solid state with increase in the Weisenberg number, and analogously we see the same also for the birefringence. So we find a quite good match in this part. And then we can go to the mixed flow kinematics, where we use the microfluidic cylinder. And again, we start with the particle tracking velocimetry, and we see at first that experiment and simulation give a good agreement in terms of velocity. And what is very important to notice is that we can observe a velocity overshoot at the rear pole of the cylinder. And this velocity overshoot is often referred to negative wake. This is a phenomenon that is not what expected in a Newtonian fluid, and just to make it sure, to make sure it's clear, that the velocity at the rear pole of the cylinder accelerates and then slightly decelerates and attains its stable value over here. And as I said, it's not what we expect in a Newtonian fluid, but it's not either what we expect in a polymeric fluid. Indeed, the polymer solution, as shown in this other paper, usually decelerate at the rear pole of the cylinder, and the velocity is small compared to the sides. And here we obtain, in our case, we are in the opposite scenario pretty much. So we have seen the development of this negative wake, but what happens at higher flow rates? At our flow rates, the negative wake disappears. And we explain this because the material attains its lowest plateau in terms of shear and extensional viscosity, and therefore lambda goes to its minimum, and the material behaves more like a Newtonian fluid. So this is more similar to a Newtonian fluid in this high Weisenberg number region. And then again we can gain some information about the simulation, about the yielded surfaces, the yielded region, and compare it with the birefringence. So what we see is that the material is mainly yielding around the cylinder, which is the region where the stress is the highest, and also near the wall, because the shear is very high in that region. And we can try to make the comparison with the birefringence, and we see that in this region indeed the high birefringence matches quite well with the area of yielded surfaces, so the surfaces that are in the liquid state. And this is because in the birefringence profile we obtained information about the alignment of the rods, and when the rods are in the liquid state they can align. And also in this region pretty much we have a good agreement in the rear pole of the cylinder. However, what is important to say is that the model predicts that far downstream from the cylinder the material regains its solid-like structure. However, in the birefringence we still see a relatively high birefringence. So at first these results appear to be slightly contradictory with each other, and what we do in this experiment is to visualize a larger portion of the channel, and we see that the birefringent wake is also present far downstream of the cylinder, that is highlighted over here. And what we do in this experiment is to flow the material and then stop the flow and measure the birefringence at rest. And what we see is that this region near the cylinder, where the material was predicted to be in the liquid state, the material can undergo reorganization, and the CNC can reorganize thanks to Brownian motion, and therefore the birefringence attains pretty much a random pattern. However, what we get in a consistent manner is the presence of this birefringence wake that is preserved, meaning that the material, when gets aligned near the cylinder, resolidify as predicted by the model over here, and the CNC get caged in this anisotropic aligned state. and once the flow is stopped, the material is already in the solid state, and therefore it cannot reorganize anymore, and that's why we obtained again the same birefringence wake, as we preserve the birefringence wake. And just to conclude, what we have seen in this presentation is something about the structural and mechanical property of the soft colloidal glass in simple rheometric flow, and also using the microfluidic Oscar device to generate extensional flow, but also mixed the kinematics using the microfluidic cylinder as benchmark microfluidic device. And we employed the TVP constitutive model to capture and the experiment, but especially to gain further information where experiments are very difficult or impossible to perform. And what we did was also a remarkable observation of the velocity overshoot at the rear pole of the cylinder, which is called the negative wake, and this was developed only when the liquid and the solid phases coexist, meaning at very low Weissenberg number. However, when we were going a very high Weissenberg number, the material behaved more Newtonian-like, and the negative wake disappeared. And finally, we have seen the flow around the obstacle, which is the microfluidic cylinder, for inducing anisotropy in the material, and this possibly can be used as an alternative of other conventional techniques that are used to produce anisotropy in soft solid, and such as the flow focusing device. And if you want to know about this a little bit more, you can Google our paper. And thank you so much for your attention.